What does correlation mean? What does relation mean?
Similarities between two things.
Similarities between two things. Close. What else?
Correlation. Two things that are alike or connected somehow.
Connected somehow. Dominic, did
Oh,
you
yeah, I was literally gonna say what connected.
They are related in some way. Correlation simply means you have one variable, another variable. They are related in some manner. So, it is only when there is an X you start wondering why. And occasionally you cry. No one got that? Fine. So y is one variable and x is the other. I like to use an example that people can relate to. Suppose you have two individuals, romantic partners, significant others, friends, whatnot. And one individual is X, the other is Y, and they have some sort of a relationship. And we would like to explain that relationship using a function, mathematically. So, f of X would simply explain the behavior of Y with respect to X as some sort of a function. Y, from algebra, you should know Y is called the
Independent variable.
independent variable. You just shattered my heart, Ben.
I shattered my own
Ben
heart.
Tim. Huh?
I shattered my own heart.
Good. The dependent variable and in literature, people call this the response. In literature, I mean statistical literature. And that is called the predictor. And it would make sense later on as to why we call that a predictor. As far as this class is concerned, we're just going to use one variable. But in practice, we could have as many as thousands, or even more predictors. But the issue is the more predictors we have, the more observations we need, or else you can't explain the relationship. Do you know why we always call the independent variable as X, but we don't call it as, say, Matthew or John or, Angela, or a person's name in general? No?
X is shorter.
X is shorter? I've got a better answer. Because if you start writing it as a function, you would end up saying f of Matthew, f of John, f of Angela. Get it? But no, we call it f of x because x, y is the coordinate system, x-axis, y-axis, and why do we default to f? Because f is simply function, like function of x. So the objective of regression is simply to identify that function, that unknown function f, that explains the relationship between x and y using samples, technically speaking, one for x and one for y, but they should always be paired. In other words, for each value of x, you have a corresponding value of y. They have to be in pairs. So that said, the underlying function it could be linear, or it could be nonlinear. What does linear mean?
It's in a line.
Did you say, is it a line?
It is a line.
It is a line. The relationship is like a line. So if we're trying to model something in a linear sense, then we use linear regression. But if we are trying to fit something nonlinear, then we should use nonlinear regression. As far as this class is concerned, we are going to use only linear regression. There is lowercase r. Lowercase r is called the correlation coefficient. What does it tell you? It tells you the key phrase here is linear relationship. You cannot use R to explain a nonlinear relationship. Of course, we can compute the value of R, but would it be accurate? No. Let's go back to the example of, two people in some sort of a relationship, maybe friendship, romantic partners, significant others, whatever. So with respect to time, and let's say it's the value or effectiveness of the relationship, I'll just call it value. Or worthiness, whatever. Before we sketch this, if I observed, say, two of my friends are in a relationship and someone's asking me to explain their relationship, so me being a math nerd and all, I am going to explain it in a mathematical way. But in order to do that, I need to collect data. Do you believe that any relationship in life, may it be whatever case, would this be like that? Is it a perfect line? No. You're setting yourself up for failure if you expect for something like that. That doesn't exist. Okay, so if I collected data, maybe I could say something like that. Yes? Over time, There were days when it hit a low, and there were days it was extremely high. And could I explain that mathematically, though? It's just a bunch of points, right? Is that a function? Could you explain it using a function? A function is a formula, right? Is there a formula that would work? No. So the objective of regression is to find something that would fit this data. You look at that, what type of a shape do you see? What kind of a pattern do you see between X and Y?
As X increases, Y also increases.
As X increases, Y also increases, but in terms of a curve, what would that curve look like?
Wouldn't it just be a line of best fit?
Huh?
Wouldn't it be a line of best fit? Where you would just put one straight line?
Let's forget about the other parts, just
Okay.
the very first part.
Line?
Line, right? Yeah, could we agree that there is a line? Yes? So this could be the line that explains the relationship between X and, or the value and X and Y in this case. If it is a line, then I have an equation. Are you playing with your phone? You are. You can put that back down. Today's not my first day teaching. So, where was I? Do we have an equation for a line?
Yeah.
Yes, okay. So if my friends, if I want to explain, would I explain this to be a positive relationship or a negative relationship? Positive. This is a relationship that grows with time. How about that one? What is the underlying shape if I have to explain it using a curve? A line still. And is that a relationship that we should pursue?
No.
No. Why?
Negative.
It's a negative relationship. It keeps on going down. The next one, we cannot lie. We've all been in one of these. If not, you will find one soon. It'll teach you good lessons in life. Okay. Now, what kind of a shape do you see? Huh?
Parabola?
That's a parabola.
Well, I said it as at the end.
Oh, parabola. So, okay. So, what, can you wave? Okay. So, right. Should you be in that relationship? Crazy. If you like crazy, you can be there. So it's a roller coaster ride of a relationship. Okay. And the last case. Is that something worth pursuing?
No.
No, but in reality though, that's like keep on chasing somebody with dreams that go nowhere. Right? Because it's all over the place. it's scattered all over the place, but nothing meaningful is going to come out of that. This is what we call pure noise. There is nothing meaningful there. Of the four, which is linear? The first two. The third clearly is non-linear. And this, we don't know. It's just noise. If I found the value of R, in this case, the value of R will be greater than 0. In other words, it is going to be positive. In that case, R would be less than 0. In other words, it would be negative. There, it could be between -1 and +1, but it is not meaningful. Can someone tell me why it is not meaningful?
Because it's constantly changing.
What?
Because it's changing constantly.
Well, this is changing constantly.
Oh, I thought you meant on the non-linear.
Yeah, but why is it not meaningful?
Because on the two linear ones, the derivative R is unchanging constant.
So R is meant only for a linear relationship. As I mentioned earlier, we can find a value of R in this case. If we plug it in the formula, we'd get an answer, numerical answer. But we can't interpret it because R stands for linear correlation coefficient. What do you think the value of R here would be? Okay. Cockney here says, not Cockney. Okay, eventually. Benton,
If we have pure noise, shouldn't R be 0?
should it?
I'd say so,
Okay.
because the strength is minimal.
R would be approximately 0.
Would it also be 0 for a horizontal line? Would it be 0 for a horizontal line?
Would it be 0 for a horizontal line? The slope would be 0, not the correlation coefficient. Because the correlation coefficient measures the strength of a linear relationship. So even if you had a bunch of horizontal dots, that explains a pattern, right? The pattern being a horizontal line. So the slope would be 0, but not the correlation coefficient. A perfect positive linear relationship would imply the value of R is 1. In other words, a perfect line. In a similar manner, a perfect negative would be R equals -1. And the third condition is R can only be between +1 and -1. Good. I want you guys to give me an example of two variables. It could be discrete, it could be continuous, that are related. Something I can collect a sample from you guys. I'll start with something really easy and simple, height and weight. But you're not supposed to use that example. Do we understand? Go ahead, Ben.
Age and hours slept per day.
Age and hours slept per day. We know one outlier in this class.
I don't sleep that much anymore. It turned out I just had a really bad infection. So I'm been sleeping less.
Oh, I see.
So it's all better now. I'm on a normal sleep schedule, 12 hours every night.
Well, maybe you should go back and get the infection again.
No, I like having energy.
Okay, age and the number of hours a person sleeps. Okay.
Age and height.
Age, we can't use height.
Why?
Just,
Because it's continuous?
huh?
Is it because it's continuous?
No, because I said no height weight, because I picked that example.
No, not weight. It's just age and height. So instead of weight, because we can't use that.
I see,
Yeah.
okay. Everyone here is of the same age, right? More or less.
You could do height and shoe size.
Height and shoe size. So, do you think as height increases, we could use an example, it doesn't matter. One more. It doesn't have to be closely related because I'm trying to find a correlation coefficient.
Eye color and hair color. You could do eye color and hair color.
Eye color and hair color, I am going to say that is wrong. Why?
It's not quantifiable. It's not quantifiable.
They're not quantifiable, they're not quantitative variables. How about the number of cats you have and the amount of sleep you get? You think that's going to be related? Who has cats? It certainly is kind of true. You want to get up at 7 in the morning, but the cat's going to wake you up at 4. Okay, which one are we going to go for? Age and height, I think we'll have very few data points. Age and hours of sleep. That's not going to be that great. How about this? I'll just say it on unanalyzed. Would the amount of food that you spend at a fast food restaurant depend on the number of pets, or will the number of pets that you have depend on the amount you spend at fast food restaurants?
Would it be per day? Or like per week?
Thank you. We'll just say per day. Is that going to depend on that? Or is that going to depend on that? Or would it matter in this problem? It wouldn't matter. By all means, I think there isn't going to be any relationship whatsoever. We'll see. I'm going to call X to be the number of pets. And Y would be the amount spent at a fast food restaurant per day. Okay. If I recall correctly from one of our previous examples, the highest number of pets per had was 7. So I'm going to talk about 5. Could be from a different box. I just need one volunteer who has no pets. Okay. How much do you spend
$3, I don't know.
per day?
Well, I don't go every day.
Okay.
None.
How much do you spend at a fast food restaurant?
None.
On average, none? Okay. What do you eat at home?
No, I eat in the dining hall.
Well,
Why did you ask?
how much do you spend at a fast food restaurant? You said none.
Yeah.
And I asked you, well, where do you eat? At home?
Yeah.
Okay. Well, we'll keep that. Who has one pet?
Like $2?
Chick-fil-A mac and cheese is only $2.
Well, I'm saying on average.
On average, I see. Okay. 2 pets.
Like $4?
I know what you guys are doing. The next person who says 6 will be failed. 3 pets.
Well, I was gonna say 6, but I guess I won't, so I'll say 4.
4 pets.
6.
Do you really want to fail? I'm going to put 7.5. How about 5? 5 pets. No one has 5 pets. I'll just say no. I'm going to work out the formula because your homework system might want you to do it, but when I fit the linear regression model, I'll show you an easier way to find this. don't be scared. It's not difficult. All of that is inside the sun. Does that remind you of something? Observation minus mean divided by standard deviation.
Isn't that for z-squared?
Is it?
Pretty sure.
It is? Okay. That is simply the z-score for the x values. So I'll just call it z sub xi for each I. And that would be the z-score for y values. So we have x, we have y. So you all know how to use one bar starts. Go ahead and, well, you don't have to find the mean. The mean is obviously 2. Put in the list and tell me what the standard deviation is for each sample. Because of that, thank you. Pay attention.
Even if the 0 wasn't there, 33 would have been 3.
No, the median would be right here.
Let's go see.
So 9, 12, divided by 6, 15.
15 divided by 6 is 2.5.
15 divided by 6.
Yeah.
Do we have the standard deviation? You can use your calculator. So we have the mean, to verify the mean, I think that's fine. Just need the standard deviation for x.
1.87.
1.87?
Yeah.
Yes, can confirm. Does make sense. How about standard deviation for y?
3.35.
So we take each value and subtract the mean and divide by the standard deviation. So 0 minus 2.5 is negative 2.5. Divided by the standard deviation is 1.87. 1 minus 2.5, negative 1.5 over 1.87. Negative 0.5 over 1.87. The next one would be 0.5 over 1.87. 1.5 over 1.87. 2.5 over 1.87. I'm just plugging it in the formula, each observation minus the mean divided by the standard deviation. So 0 minus 5.3 is negative 5.3 divided by 3.35. 2 minus 5.3 is negative 3.3 divided by 3.35. 4 minus 5.3 is negative 1.3 divided by 3.35. Same. Seven 7.5 minus 5.3 is 2.2 divided by 3.35. 3.7 divided by 3.35. Yes? We don't want to write everything or divide by 1.87 for each term. It's not necessary because these two are constants and every single term has 1.87. And if you recall factoring from yes.
For the mean for y, my calculator got 4.4.
4.4. Is that 4.4?
Yeah, I also got 4.4.
Keep forgetting that 0, I'm sorry. She waited until I was done with everything. Then you're wrong.
I mean, my hand was raised for like the entire time you were writing that one.
So, negative 4.4 divided by 3.35. Negative 2.4 divided by 3.35. Negative 0.4 divided by 3.35. Same. 3.1 divided by 3.35. And 4.6 divided by 3.35. So every single term here is divided by 3.35. Every single term there is divided by 1.87. So those two numbers are constant, so we could simply pull it out of the sum. So outside the sum, I have n minus 1, 6 observations, so n minus 1 would be 5. From algebra, if you have a common term out, you can just pull it out. So 1.87, 3.35, they're in the denominator. I'm going to write it back there. So that would be the n minus 1 part. That would be Sx, and that is Sy. And we have to sum through all i's and multiply the differences, xi minus x bar. So the numerator would correspond to the difference between the observation and the mean. So the first numerator is negative 2.5. The yi minus y bar, just the numerator part, right there. Plus, because we are summing over all observations, plus negative 0.5 multiplied by negative 0.4. .5 multiplied by negative 0.4. Okay. So let's go ahead and compute that and divide by that number and tell me what you get.
Did you do
0.9824. Is that believable? If you say yes, you got to tell me why. If you say no, you got to tell me why. We got a linear correlation coefficient of 0.9824. Is that believable, Benton?
It is believable because it is a strong positive correlation. As x increases, y increases, and as x increases by some set amount, y increases by some close set amount.
Okay. Did we follow what he said? Now, clearly you guys tried to game me at the beginning, right? You sort of picked up the pattern, but that's okay. So that's why I said don't give me 6, right? Because 0 times 2 is 0, 1 times 2 is 2, 2 times 2 would be 4, and pretty much the slope would then be 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. What is the slope of the line? 2. But I didn't want that. Because that would be a perfect relationship. Excel can give a plot, but doing this for the purposes of illustration, so first observation, second, third, fourth, 7.5, probably right there, and 9. That looks pretty linear, agreed. So we should expect a value close to 1. So that particular number is believable. We have a positive relationship and it is increasing. Now the question is, what is the equation of that line that would describe these points? Maddie said, oh, it is the line of best fit. Why did you use the terms best fit?
Because normally if you have like a plot of data, you would pick a line that's nearest to the middle, like touches the most points. So it's like in the middle of the data. So
That is correct. If I asked you, well, explain a line, if we find the line, then we have an equation, correct? So what would explain the line best? Well, how many lines can I draw through these points that would explain the relationship well, technically speaking? How many lines can I draw?
one.
Just one? Okay. You don't have to draw this, but I'll do it. So I could draw a line like that, yes. I could draw a line like that, yes. I could draw a line like that, correct. And I can keep on drawing lines. And I could draw a line like that. Hypothetically, which line's the best?
It would be the first one you drew that goes through 3 points.
That one? Okay. I mean, what's your name? Ethan. Ethan says it should be that one.
I believe the red dotted line is the best because it reduces the amount of displacement between all of the dots.
Displacement. Fancy word there, Benson. But I understand what he's saying. So I will explain what he is saying later on. So the dotted line is the best. The reason for that is by displacement he meant the distance between the line and each observation. So if you look at the distance between the line and the observation, the least amount would be from the dotted line, okay? So if we have a set of points that look like a line, I could draw infinitely many lines. But out of all those infinitely many lines, only one line is the best one that would describe the relationship well, which is why we call that dotted line as the line of best fit. Good? There can only one that would be best. Are we clear? So Regression tries to find an expression that, or a function that relates y to x. Linear regression tries to come up with that linear function. That linear function geometrically is the line of best fit. With me? So there is this entire process called least squares regression that is not required for this class. So we can jump into the model itself. Can I erase this? Different books use different notations, so I don't know what your book uses. I'm going to use the standard notation. But when we say equation of a line, what is the format? Algebra. Who took algebra? Everyone? Okay. What is the equation of line? Y equals mx plus b. So I'm just going to write y equals beta naught beta 1 x plus beta naught. Okay, so the goal is to find beta naught and beta 1 using data. This is the same as saying y equals mx plus b. This is why we taught you algebra. Now you may say, well, why do I need statistics? Eventually this is going to play some part in some science if you get into science. It is also used in business. So the traditional notation is beta naught and beta 1. Beta 1 would correspond to the slope and beta naught would correspond to the y-intercept. So our objective is to find beta naught and beta 1 using the data. We don't have to go through the derivation and, you're interested, take a math class or a statistics class in advance. But if we put a hat on top of a variable in statistics, it becomes a or an. Long time ago, we went over this. Remember that bad joke about myself? I said, when someone asks me, hey, Peter, why are you wearing a hat today? I tell them I feel like an...
I definitely don't think you need to.
Estimator.
No.
What do you mean? Mu hat? Look in your book. Mu hat, p hat. We didn't do it?
No.
Okay, fine. I have to edit that out of the video.
Wait, I don't have to do it.
I thought I did this. It's okay. I'll let it go. So, an estimator for that beta 1 and estimator for beta naught. Why do we call it an estimate? We don't ever know the true values. In other words, the parameters in statistics. we can only come up with an estimated value using the data. So I'll jump right into the formula. The formula here is R multiplied by the standard deviation of Y divided by the standard deviation of X. So you can see if I used algebra, that equation will work out. So all we need to know is the standard deviation and the correlation coefficient. If we know those values, then we can find beta 1 hat. And we can make use of the means of the sample and beta 1 hat to get the estimated for beta 0 hat, which would be the y-intercept. The line of best fit will definitely pass through the average of the x values and the average of the y values. But by all means, which that is the reason why we call it the line of best fit. That goes to the derivation part of things. So, in other words, in our previous example, the average was 2.6 for x, yes, and for y it was 4.4. 2.5. So 2.5 and 4.4. Look at that. It passes through. So it has to pass through the average x bar and y bar for it to be a line of best fit. Good. So that is the formula. You don't have to memorize it, put it in your cheat sheet. Who would like to give a good example of a paired sample, x and y, so that I can collect a sample here? Benson.
Height and walking speed.
Height and walking speed. Okay.
We do height and the number of years you played sports.
Huh?
Height and the number of years you played sports.
Height and the number of years you play sports. Okay, that's a good example. Let's make both of them continuous. Continuous variable for x and continuous variable for y. Someone said, I think it was Josie, you like to spend time at the beach, right?
Yes.
So how do you measure the level of tan? Is there like a scale? No. Just look in the mirror and like, oh look, I'm tan. Okay, so that's not going to work. So the time spent at the beach T is linearly related to the level of tan. I'll just call it Y. I'm going to make it continuous on a scale of 1 to 10. We can measure it with some sort of machine. So that is going to be a continuous variable. 1 would mean you spent a lot of time, you're still pasty white. And 10, you got a real good time. Does that make sense? Any value in between is doable also. I know friends who go to the beach and they want to get tan. At the end of the day, they're just sunburned. Okay, here is the question. Would the level of tan depend on the time spent on the beach? Or would the time spent on the beach depend on the level of tan? Idealistically speaking.
Level of tan depends on time for the beach.
Very good. So the amount of tan that we're going to, or person's going to gain is going to depend on the time you spend at the beach. So Y would be level of tan, and T is the time spent at the beach. Typically we go for hours, so we'll make it in hours. That one doesn't have any units. I can make one up, but don't want to. So here is the sample. So we're going to collect a sample is collected to obtain a line of best fit that describes the relationship between Y and T. Six hours normal Jersey.
Depends on the day, the time of year, for real.
Okay. Put 5 and 6.5. What do we expect to happen? Should it go up, down? We account for physics and chemistry. What do we expect to happen? It has to go up. So let's just say 1.25, 2.9, 3.4, 5.6, 6.2, 6.7, 7.5. Now keep in mind, this particular sample ignores a lot of things. For example, the gender of the person, the health conditions of the person, the race of the person. I'm just hypothetically making this up. In practice, this wouldn't work because there are other factors that we need to consider. Okay, so 1.5, 1.25, 2, 2.9, 2.5, 3.4, 4, 5.6, 4.5, 6.2, 5, 6.7, 6.5, 7.9. Good. Our objective is to find or estimate the values of beta 1 and beta 0, which would be the estimators. And how do we find this? We use the formula to find them. So I guess I'll leave that as homework. I want you to try the formula. It is very straightforward, yes? Plug it in the formula and see if you can. We know how to find R. We know how to find SY, SX, and use all that to find the line of best fit. If you can't find the line of best fit, please find the mean and standard deviation before you come back next time. And I'd also show you how to do this using the calculator. Good. If you have any questions, talk to me. If not, I will see you next time.